Okay. Try to add the link. Yes, I started. I started recording. I started recording as well.
You can attach a pen because it gets no. Because attach here a pen and
I don't have a pen. Do you have a
pen phone. Everyone has a pen. Yes.
It's not very professional.
Yeah, you can attach it until we are not professionals. Okay, do this one. That's enough. So how is it? Enjoy. So is it well? Funny. Better? Why not? No, it's perfect.
Now it's better.
Ah.
Doesn't change so much. Well, there were.
Yeah.
Settings.
But now
Now I
standard.
don't know.
Let's go.
Here? Camera view.
And here, can you change anything?
Not things like
Why volume is
luminosity,
zero?
because otherwise it will record. I'm gonna set it back when it starts.
Okay.
Bad push.
What?
The speed is kind of bad. Why is it bad? Keyframe frequency 6 seconds. It's because it's
Oh, it's
Wait, it appears okay.
Can you turn on the sound? Let's check the sound.
So if we're checking the sound, it probably be best if we had some headphones. But I have upstairs something.
Oh, it's fine. Yeah,
Yeah, I'm turning on the sound. Don't say anything stupid.
it's fine. You can say. It's fine.
You can skip, for example, you can make a people and you can't skip in the middle because this doesn't know
Володя.
No, so everything
Walk everyone trying to...
sorry, to make them sound I was actually directing university.
Very professional. It's a very professional setup. I know.
Yeah, I also went to oh, right.
Let's start our afternoon session, and the first talk will be given by Tim the Q4 superstring. Please.
So thank you very much. First of all, thanks to the organisers. I'm a bit of a nuisance. I turned up a little bit late, and also I changed my title somewhat. But thank you anyway. So I want to talk about some work that I've been doing off and on for a few years with various collaborators. Ben Hall, David Schmidt, and my student Callan Apadu. So this talk is all about deforming in a certain sense, and it's a very natural thing for us to do as physicists. If we have something very special, and for sure the gauge gravity correspondence or duality is something very special, then we like to explore its definitions from different points of view. So there are different kinds of approaches to definitions. So we might think about definitions of the dual gauge theory. We might be interested in less supersymmetry, something that looks more like the real world, but obviously that doesn't interest us here. We might be interested in definitions of the space-time of the Erasmus. We might find that interesting, but obviously not. We're here because of integrability. So another kind of definition is to think about definitions of the integrable structure that lies behind the gauge gravity correspondence, and that's what I want to talk about. Now, usually, I think that integrability is a very rigid concept. It's very special, and we would imagine that any kind of definition would generically break integrability. But in another sense, integrable systems have a huge amount of flexibility that normal systems don't have. We just take a simple integrable equation like the MKdV equation. So that's the MKdV equation. Now this equation can be written in Hamiltonian form. So there's a Poisson bracket and there's a Hamiltonian which gives that equation in motion. But actually, freedom here, because there are actually an infinite number of possible Hamiltonians, infinite number of possible Poisson brackets. So you can use these new Hamiltonians, these HIs, to define different notions of time, because they give rise to flows on the phase space. So there's an infinite set of Hamiltonian flows. Or you can take the original flow and write it in terms of the new Hamiltonians with a new Poisson bracket. So there's nothing there. And in fact, you can take all this and take linear combinations of the Poisson brackets and the Hamiltonians and define new notions of flows.
Tim, it's still the same theory. You haven't done anything.
Still the same theory, good. It's the same integrable system. Okay? But actually, for us, we think of maybe a theory in terms of something defined with a Lagrangian in action. And more interestingly, I suppose, is can these kind of definitions of, say, the Poisson brackets or the Hamiltonians be realized in field theory? Now, so that's one aspect of definitions in integrable systems. There's another more specific idea of a definition, which is ultimately related to the one above. That is that often, the quantum field theories we're interested in have symmetries, global symmetries, described by some Lie group F. And in an integrable field theory, these global symmetries are actually part of a bigger structure, because there are all these high spin conserved charges. So they form something that's bigger than the Lie group or the algebra. They form a structure called a ganglion, typically. Now, there's a way to deform these ganglions that's kind of well known in the integral system literature, and that is to deform them into something called a quantum group. Quantum groups are deformations of the algebras, and there's a deformation parameter q, and the ganglion is somehow recovered in the limit where q goes to 1. Naturally, 1 plus 1 dimensions, particularly in theories with local symmetries, because the symmetry charges have non-trivial monotony. In 1 plus 1 dimensions, there's only one space. So if I have a product of two local operators, they're 2 points along the line, and if I'm acting on that with a symmetry charge, it can act on the first operator, but then because these operators have to be defined in a gauge-invariant way, they have to be dressed with something non-local like a Wilson line, and then these symmetry operators can't get past, well, they can get past, but they leave something. This theta here, if you like, is the monodromy of the jet in 3 plus 1 dimensions that lead to these structures of quantum groups. So we've got these sort of two ideas of deforming. Now, let's think about string theory at the level of the world sheet, particularly in this iconic case of the string moving in ADS5 plus S5. And it's been known for a long time that if we look at this theory around this particular vacuum state where the string is point-like and going around the equator of the S5, and it has equations of motion which are equivalent to a generalized Sine-Gordon theory. So in some specific cases, smaller dimensional spheres, it actually is Sine-Gordon theory this morning. So this string world sheet theory gauge fixed in a super, which actually makes it non-relativistic, is equivalent to a relativistic quantum field theory, this Gordon theory. Of course, this is the Polymer reduction. So this was the thing that got us interested in this subject to start with, because these generalized Sine-Gordon theories are interested in quantum field theories in their own right. Okay. Obviously, these theories are different, so the classical equations of motion can be the same, but they're different as quantum field theories. For instance, the S matrix that describes excitations on the string world is described by some rational R matrix, some solution of the Yang-Baxter equation associated to a Yangian type symmetry. Whereas the Sine-Gordon kind of theory has an S matrix which is naturally described by what's called a trigonometric R matrix, and those are naturally associated to quantum groups. In fact, it turns out that particular Sine-Gordon theories correspond to quantum groups where the deformation parameter is the root of unity, and those cases are very special. So the original idea is that the Sine-Gordon theory describes some deformation like string theory. That at the classical level, it turns out can be thought of as a deformation with Poisson brackets or some symplectic structure. So you see it realizes this idea that I had at the start. Okay, so let me say a little bit more about this world sheet theory. There's actually a very natural way to deform that non-relativistic world sheet S matrix, which is described by this rational R matrix. I mean, I won't go into too many details here. So you can deform it by replacing it by some trigonometric version. So this is the trigonometric R matrix that Y is the product here. And so we thought about that solution of the action, this deformed one, and we constructed an S matrix based on it. But the S matrix we constructed, so in principle the deformation parameter Q can be real, can also be a phase complex, but we looked specifically at this case where it was a root of unity because we had in mind that it was going to be related to the Sine-Gordon theory. So the S matrix was only this. And it turns out that's particularly interesting because the K here is some positive integer. And the S matrix is particularly nice for this case. In fact, really, this is the only case we considered because it has a finite spectrum. And there are different ways to write the dispersion relation of the states in this S matrix theory. It's a non-relativistic S matrix theory, so the dispersion relation has this funny non-relativistic form. This is how I like to write it. E is the energy, P is the momentum. Here's some combination of the couplings in this theory. There's the K, which is the, if you like, deformation parameter, and G is the sigma model coupling of the world sheet in the original theory. You can think of that as being the top coupling in the gauge gravity correspondence. And the states in the theory are labeled by this integer, which is truncated. It runs up to k. And this arises because of the special properties of quantum groups, roots of unity. And in fact, for a given Q, states transforming representations of the global symmetries. And it's a kind of interesting S-matrix theory. There's all the usual axioms that used to in relativistic theories, except that obviously it's not relativistically invariant. And that has some interesting effects. For instance, states can become unbound when you boost them. That's something we're not used to in relativistic theories. I just want to mention two limits of this S-matrix before I go. One limit is where the k, which you can think of as being the deformation parameter, although it's actually an integer, so it's a funny kind of deformation. When this gets very, very large, this dispersion relation reduces to the familiar one of the string world sheets. So these describe the so-called dynamic giant magnons. The other limit is where g goes to infinity, the coupling on the sigma model. And in that limit, you get a relativistic dispersion relation from here. And that's precisely the dispersion relation of all these generalized sign-Gordon theories. So we have an S-matrix that sort of goes between the string theory, IGST5 plus S5, and then this relativistic sign-Gordon theory, or kind of generalization thereof. So the question was, it's all very well to have an S-matrix, but what are we actually doing here? What's the underlying theory? What's the Lagrangian description? And in fact, there's an old clue that I'll mention, and that is that the principal chiral model, we take the simplest, corresponding to the group SQ2, it admits several kinds of integrable deformations. These were described a long time ago. Now, one of them involves taking the S-matrix of the principal chiral model, which involves the product of two R-matrix factors, one for the SU2 that acts on the group to the left, and another one which arises because there's a symmetry of group action to the right. So the deformation out of the class, the several classes, is one that deform at the quantum level, deforms the S-matrix by taking this and deforming, say, the right action into the quantum group. So this thing here is the normal, in fact it has a Yangian invariance, and this gets deformed, at least one side of it gets deformed into the quantum group. And in fact, well, I could talk more about that, about the spectrum of particles. For instance, in the principal chiral model, the states transforming the two-dimensional representation of SQ2, one for the left, one for the right. Whereas in the deformed model, it's more natural to describe the quantum numbers in terms of kinks rather than spin up or spin down. Now, the interesting thing from our point of view is that the ultraviolet limit, this massive scattering theory, when you go to this deformation labeled by K, is no longer a free theory. So the principal chiral model is asymptotically free, but these theories are not. The ultraviolet limit is actually an SQ2 WZW model deformed by a current operator, which is marginally relevant. Okay? So this construction and all this analysis was just for SQ2. And the natural question was how to generalize that to a general group who didn't know the answer to that. So we had to wait later for the answer, which I'll show you in a second. So let's talk about these sigma models more generally. The chiral model for SQ2, the whole class of integrable sigma models based on symmetric spaces, some quotient of group G, and what's special about symmetric spaces is there's a Z2 grading of the Lie algebra of F, which is respected by the Lie bracket. And one way to formulate them is in terms of a group value field in capital F, this is little f, and a gauge field that lives in the subgroup G. So this is what you write down as an action, where this current J is the familiar thing here, minus the gauge field. The equation of motion of the gauge field is then a constraint that says equals the zero component. So that, I didn't say that, F0 is the Lie algebra of G, the thing that lies in denominator of the quotient. The equation of motion of F is this condition here on J, where the covariant derivative is described with respect to the gauge field B. But we can write a set of first order equations by introducing the Cartan-Maurer condition, which is just, if you like, a flatness condition for the current, which implies that there exists an F such that this J is a pure gauge. So these are the equations of motion written in this so-called first order form. That's a useful way to write them, you'll see in a minute. Now, integrability at the classical level follows because you can write these equations of motion in lax form. I'm not going to really use that here, but it's very easy to write a lax connection. And that, more or less, proves integrability at the classical level. So the old SU2 result that I mentioned motivates defining this K-deformed, if that's the right word, theory in terms of the perturbed WZW model more generally. And in fact, the way to do this was discovered by Spetsos. I'm going to describe it for the case of these symmetric spaces. So what you do is you take a WZW model for a group F, so that's what this curly F field is in F. Then you gauge the whole of it. So you've got a gauge field that also lives in F. It's the vector subgroup, which is the anomaly-free one. You write down the action. That would be the action there. If that omega there is just 1, that would be the action for a gauge WZW model. But it's not 1 because in the components, the coset directions, you deform that term by introducing the lambda, which is coupling. Now this theory, because we've deformed it in this way, it doesn't have the gauge symmetry under F, it only has gauge symmetry. The field is 0 component of A. If you like, the component in the coset direction is now just an auxiliary field. It appears in the action quadratically with the integrated out. Now, as lambda goes to 0, in fact this was matches up with something that Ben mentioned this morning, we can think of this theory here as a current deformation of a coset CFT, so F at level K over G at level K, by an operator of dimensions, a relevant operator, so dimension less than 1 here. H here is the dual Coxeter number or the quadratic Casimir in the adjoint. So this action here reduces as lambda goes to 0 to this. Now you might that's a marginal operator because we have to move current. It's to do with the fact that this is in the coset directions, and for gauging variance, you've got to address those operators to make the gauging variance, and that shifts the dimension from 1. Okay, so that's what our theories are. Now, particularly important from my point of view is that we can take this theory and we can write its equations of motion in first order form. So the way that we do that is we take the equations of motion of the gauge field, we get these two constraints here, and the equations of motion for the group field F can be written in two ways, just related by conjugation by FF inverse. And it's a nice way to write the equations of motion because then the combinations that appear here appear in these constraints, so we can make the substitutions, and then we can write the equations of motion in first order form like that, purely in terms of the gauge field. So the group field is in there through these constraints, you see. Now, if we stare at those equations, you can see they're exactly the same equations of motion of sigma model I talked about, which apparently has no relation to this theory, but now we see that it does because it's got the same equations of motion, at least with a kind of rescaling by that parameter lambda. So this is, if you like, the dictionary. But the theory has different Poisson brackets. I'm not going to talk about Hamiltonian analysis, but Poisson brackets are different. So the classical limit is taken where the sigma model coupling, the way I define it, goes to infinity, k goes to infinity, but you can take a ratio, this kappa squared and k fixed, and you have a one parameter family in Poisson brackets. And the limit lambda goes to 1, the WZW So the deformed theory, compared with the original sigma model, has two parameters. A, which controls the loop expansion, and it has this lambda. And the thing we want to really know is, how does this lambda behave quantum mechanically? K has to be fixed, of course, because of the usual reason to do with the Vesselino term. It has to be quantized. But what about K? So what we want to do is calculate the beta function. And so let me describe how that goes. This will be in a paper with my student, Callan, to appear very soon. The idea is, well, there are many ways to calculate a beta function, but these theories are a little bit complicated, so we want a really, really simple way. One simple way is to take a classical solution and calculate the spectrum of fluctuations around it, which you can get directly from the classical equations of motion. That gives you a renormalization group equation, which, see, this is the Lagrangian, or it's the Lagrangian density evaluated in the classical solution. The fluctuations contribute, we get the log of the determinant. So that's the term here. And in a simple case, we just get the fluctuations just have a spectrum of masses, which would be a function of decoupling. And we pick off the log divergence here, expand the log, get terms like the mass squared and the momentum squared. Those would be log divergent, and that's what contributes to the beta function we want to loop. So we get an equation then for the beta function. So I'm going to calculate this beta function for the original symmetric space sigma model, nothing new in that. But now, also for this so-called Q deformation, let's just do them side by side. So the method says we pick a particular background field. Here's a simple one. In the sigma model, it's little f. In my WZW model, it's this curly f. We choose similar kind of background field where we take constant elements, this capital theta, capital lambda, in the coset directions, have them commute. So then the Lagrangian evaluated on the background field is just very simple. In the WZW model, there's some lambda dependency here. That's important, of course. And then the key step is to investigate the fluctuations. But if we do it in this first order formalism, I've just shown that the theories have the same equations of motion. So basically, we only have to do one calculation. The equations of motion are the same as long as the background fields are related by this dictionary, which sort of relates the thetas to the lambdas. And then, well, those are the equations of motion there, written in terms of the sigma model current. And so we look at the fluctuations around the background field. That's described by this operator, where the thetas here are defined by adjunct action. And it's very easy to then calculate the log divergent term, as I sketched, and pick off the log divergence. And perhaps not surprisingly, it depends on the trace of the square of the background field in the adjoint representation. It can be written in terms of the normal defining representation, where we pick up the quadratic Casimir. The important point is we can use that result in both theories, the original theory and the deformed one. So we get two RG equations, as written there. Therefore, we get the beta function of the original sigma model, which is this one. And we get the beta function equation for this new coupling lambda here. And in fact, that equation then matches precisely this CFT expectation. I said the limit lambda goes to 0. It's a current deformation by a relevant operator with a certain dimension. And that dimension matches this. This is the anomalous part. So that just gives you some confidence that, well, we haven't screwed up. Many years ago. There are other ways to calculate these beta functions, but this is a particularly simple one and exploits this fact that these two theories, the original and the deformed one, have the same equations of motion. So here's a picture of what's going on. In the original sigma model, it's an asymptotically free theory. There's a coupling that runs from the Gaussian fixed point. The way I define the coupling runs from 0, it gets larger. This is the theory with the Yankeean symmetry. Now these deformed theories, they're these WZW models plus current deformation, So they're labeled by an integer k, and as k gets very large, in some senses we get similar to this theory. But at ultraviolet limits are different. They're actually non-trivial CFTs. And of course, the operators are relevant, so the RG flows flowing out of those theories, out of those fixed points, rather. So that's the picture for the bosonic theories. Now, of course, if in the stringy context, we don't just have a bosonic sigma model, we have one of these very special sigma models with fermionic degrees of freedom that's described by this semi-symmetric space. So now, in the quotient F mod G, for this particular case, the iconic one, F now is a supergroup, is SBU 2.2/4, whereas the G in the quotient is still a bosonic Lie group. So I want to apply all these ideas to the real string theory case. So semi-symmetric spaces are very interesting. They have one of the properties of symmetric spaces. In particular, they have a particular grading, but now it's a Z4 grading. And the fermions live in the odd graded parts. The bosons live in the even graded parts. In fact, the even graded bits are precisely a normal symmetric space, which is precisely what ADS5 and S5 are. And the action, of course, we've known this for a while, is this very particular combination of currents. So the bosonic ones are just like we would have bosonic symmetric spaces, but the fermions will appear in this combination here. And the equations of motion in first order form, okay, there are lots of equations, they look complicated. The more you realize they're not so complicated. They're written here in terms of all the components of the basic underlying current and the gauge field, B. So we've got all those equations, but they can be packaged up very nicely in terms of a lattice connection, which shows that these theories are integrable, at least at the classical level. So that's a very beautiful property of these symmetric space sigma models. Okay, so now we want to move on to what's the definition of this in the sense of these K theories with an integer K. So, as before, the definition is going to involve taking it to the WZW model for the group F. But now the group F is a supergroup. So it's the whole PSU 2.2/4. We gauge the whole lot of it. And we write down the gauge Vessamino-Witten model for that. Except that in the term involving A plus A minus, we stick in this object omega. And, well, if this lambda here, which is the deformation parameter of the W is 1, obviously we would return to the original WZW model. But so lambda is the deformation parameter from that point of view. I'm not quite sure why that system or that. It's interesting. Now this theory, it looks like it has a chance of being describing a well-defined string background because it has the appropriate amount of kappa symmetry. In fact, that symmetry appears as a kind of deformed remnant of the gauge symmetry of the original F mod F WZW model. For instance, here's a bit of it. So the change of the group value field under an element of the algebra valued in F1 is like this. So there's left action, a right action, but you have to multiply by this lambda. And the parameter here has to commute with this element of this bosonic element. So that kind of thing is familiar to people who know about this kappa symmetry. There's a similar thing for the element of the algebra in F3 as well. However, if the theory is to define a consistent string theory, we require that this lambda is a marginal coupling. Its beta function should vanish. So that's what I'm going to argue. I'm going to calculate the beta function in the same way that I just did it for the bosonic theories. In fact, you can probably already guess the result because of the way. So we know that the kappa, the original Green-Schwarz sigma model, doesn't run. And given what I said about the beta functions work in the bosonic theories, this is already tell you that a lambda is not going to run. But just to put a bit of flesh on the bones of that, so we use this simple background field method. So we choose our group value field in the WZW model. I've got these, no, I think that's the right. So this is the original Sigma model background field, and this is the background field in the WZW model. These are both constant elements in F2, where the two components commute with each other. Now here's the important thing. As previously, the fluctuations satisfy the same equations. Actually, I didn't show that, but in this WZW model, if the same thing happens, that the equations of motion in first order form are the same as in the original Green-Schwarz Sigma model. So we're going to get the same log terms, log divergent terms, use the right dictionary between the background fields. In this case, this is the appropriate dictionary. So now we can assemble the elements of the calculation. First of all, because I chose my background field in F2, the bosonic and fermionic fluctuations decouple, and the bosonic ones are just the same as in a normal symmetric space. So let me write it like this. The fermionic fluctuations can be calculated by looking at those first order equations and calculating the definition around them, the fluctuation around them, and they're operator here. And a bit of this operation is responsible for a log divergence from the fermionic fluctuations. Not difficult to show, in fact, gives terms that involve traces of theta squared, but now in the fermionic bits of this Lie superalgebra. So this is we get this combination here, which is precisely the supertrace in the Lie algebra. The fermionic ones coming with the minus sign, using the supertrace. And when I relate that, or I think about what that is, it actually vanishes because the killing form of PS U2.2/4 vanishes, or the dual constant number vanishes. It's a special algebra for which that's the case, and that's responsible for the vanishing of the log divergences both in the Green-Schwarz Sigma model, but also in this definition. It's the same story. So both in the original Sigma model and in this definition, lambda doesn't run, well, at least the one. So that's a clue that, maybe these deformed theories really are defining consistent string backgrounds. So here's the picture. It's just like the bosonic case, except now the couplings are marginal. So these lines here define lines of conformal field theories. There's no RG flow. Another thing I should point out is that in the bosonic theories, as this lambda goes to 0, if we go backwards against the RG flow, in the bosonic theories, we've got to a WZW model, a co-set model. But in this case with the supergroup and the super algebra, we don't. There's a finite bit as lambda goes to 0 left over. So the UV limit, well, it's not a UV limit, it's no RG flow. So the lambda goes to 0 limit isn't just the WZW model in this case. So I'm sort of basically done. So this, let's call it ADS5 plus S5K theory, where K is this integer. It seems to be consistent. No idea what it really corresponds to. From a supergravity point of view, it should be described by this supergravity background of these fine people here. They constructed this looking at a bosonic truncation of the deformed, making a sort of very credible ansatz. So it should be this supergravity background. It's not a very, well, it's got no symmetry, so it's a tricky thing. The other thing I should say, importantly, is that the thermodynamic beta ansatz side of this deformed theory has been developed some time ago, actually. So these deformed theories seem to have a lot of the structure of the original string theory. But the biggest question is, can the deformation be interpreted as doing something to the dual gauge theory? I don't know the answer to that, but the guess would be that you've got to take the Yangian symmetry in the H theory side and deform that into the quantum world in some way. Whether that's a nice thing or not, I don't know. And finally, just like to say thank you.
So you have shown that you have no UV divergences, but you start with first order formulation.
Just a one way.
Yes. In general, you need to require conformal effects or wild effects. So that means you need to decide about dilaton.
Yeah.
And you had a suggestion about dilaton in your paper. If you just formally integrate a gauge, if you integrate gauge field.
Yeah.
Like in usual with gauge Casimir model, you get certain dilaton from integration. And naively, it's not the same dilaton which is assumed in this paper by Walter Spetzes and Thompson, which has to do with the fact that they are considering just, at least the hint is that they consider non-abelian TQ just in bosonic direction, while actually, so I think it's a good puzzle which is right.
Yeah. I mean, I agree. It's a good puzzle. Yeah. I don't have any more to add to that. Yeah.
Sort of related question is just about this, the lambda K model in this superset situation.
Yeah.
Do you have any, what are your ideas, or do you have any ideas about why this should take some sort of Green-Schwarz form, in particular with regards to the fermions? Because naively it looks like you have fermions dp type things appearing from the kinetic term, which you wouldn't have in a Green-Schwarz.
Do you have what's through?
Just fermions of kind of dp to dp type fermions appearing with no bosons, just on their own. From the kinetic term of the Weissman-Witten part, which wouldn't be there in the usual Green-Schwarz search.
Well, maybe this, I mean, see, it's not quite the Weissman-Witten model, you've got this thing. So we should discuss that.
But you don't have immediate ideas of what? In your paper, say what?
No. I suppose that's the short answer, isn't it? I think it's a good talking point.
So at the start, you mentioned that in this before picture, you're really considering your scattering states before by kings. But in the regular string, I'm used to thinking of just a bosons and a fermions as a scatter.
Yeah.
So how does that relate to taking the unformed limit? Right? Is that somehow a reflection of maybe something related to this non-unit geometry, or should it be something else?
I mean, that's the way I think about it. It should be something to do with that. So, if you take one of these kink theories and you take, so the set is truncated because of this, that k is finite. As you take k goes to infinity, you sort of become unrestricted. And then that should naturally be, you would think, be related to the original picture of the S matrix, which is called the vertex picture. I think that vertex to kind of IRF picture is somehow a reflection of duality. But I don't know quite how to make that concrete. That's the kind of idea I have in my mind.
Yeah. Now on that, this is one should not forget that also that the theory in this case is defined in terms of Weissman-Witten axioms, and that implies that if you want to discuss kinks or solid conformations there, the boundary conditions are going to be quantized. So the boundary conditions are naturally, a finite number of values. That doesn't allow you to recover immediately the complete IRF picture, but at least the fact that missing some details from
Yeah, I mean, Lewis's point, is that the boundary conditions in this theory naturally mean that soliton excitations, as if I described as cubes. So I didn't have time to talk about that. You can construct the S matrix of these theories that were constructed a long time ago by Arne, Bernard, and Leclerc, and they're described in terms of kinks. And that's natural because the WZW model requires particular boundary conditions, plus or minus infinity.
So, in the bosonic case, there is an asymmetry of the action of the lambda before model, which has to do with the inversion of the coupling and the inversion of the element, something like this.
Yeah.
Do you have something similar in the superposition case?
Well, actually, already in these gauged models, you don't have this symmetry. So the symmetry you're referring to is, it's when you look at the definition of the principal curve.
The symmetry of the beta function equation is clearly invariant under lambda inverse and k goes to minus k.
That's true.
So,
Yeah.
but I'm talking even before, at the level of the action, there is a symmetry that's enhanced by the inversion of the group element. I was wondering if in the case you have something similar, because there you have extra terms.
Let's talk about it. Yeah, that sounds interesting.
Maybe a quick comment on that. The answer is yes. There is such a symmetry, which is, yeah.
Thanks, Ben.
Another maybe slightly negative question, but in the original starting point, it's supposed to be with quantized.
Yeah.
You do symmetries, and then if you form radical symmetries, is it? I mean,
No,
should it be?
No, so in these theories, and you've always got the best amino term there, so K will always have to be quantized. You can integrate out to the H field, you can write it as an effective sigma model, but the underlying theory has to be defined by the best amino model, so K will be quantized, even though it can look like a sigma model where K isn't.
Okay, if there are no more questions, let's go to the next talk.
Hello. Hello. Hello, so I suppose this work. So first of all, I would like to thank the organizers for inviting me here, and also would like to thank for this perfect logo for the conference. I really appreciate staying here. And actually, the first thing I did when I came to London is take subway to come here. And even then, after a session, we go to this room. I feel like it's a while again, and all this Mickey Mouse people was walking slowly to the room. So today I will speak about quantum spectral curve, mostly for this 554 integral system. I will try to locate that there is some conceptual equation behind it, which is basically says that some analytic change of his system is equal to some algebraic change of his system. And it's underlying conceptual idea behind it. I will start from quite far away and discuss not actually IGST15 case and discuss like most conventional general models, LTVC for instance, where there is a very common comforting property that the time of spectral parameter is meromorphic. What do I mean by this? For instance, if you have Young-Baxter equation. In this simple case, this Young-Baxter equation is this way, and we have our matrix simulated at U, at V, and also at U shifted by minus. So when you write equation, you see that if you know our matrix here, somehow if you shift it here, you also know what happens. But it's not real property that you assume. You assume now that function is meromorphic. Another example is closer to this story, is Y system. This is a C and Y system. So on this line we have many nodes which know we have Y functions, Ys, and this is standard Y system equation. And this is non-local equation. On the left-hand side, the same Y function is given U minus I1 and U plus I1. This equation, we silently assume that if you know function is the vicinity of this point, then we know how to go here, and the answer is somehow unique. If it's not, then what if you write here at all? It's not defined. So it's very important to say, for instance, if you write this equation, we say how to find this point. And only in the case of functions of meromorphic, there is no question how to do this. Any way combination is good. And if you know that we actually have a problem, and that question stress now, what is the dependence of spectral parameter is not meromorphic. And there is actually a branch point there. This means that going from this point here on green line over blue line gives different answers. Then when you write the equation, you have to be more careful what do you need. Okay, so when we encounter this situation, there are several things we can do. Like, if we want to do, oh, this is a bad variable, this is a bad variable. Let us find good variable where there are no branch points. So we find some universal monetization where there is no branch points. Well, other thing people try is say that, okay, these branch points are not really there, they are just an efficient phenomenon. So this some of the line, I think, without branch points. Other thing we can do is to learn this log is branch points. So historically, people in IGST15 we have branch points. Historically, people try to do this. So already we have branch points coming from this special relation. The most common by now what we are in special relation is through Jakovsky variable. So Jakovsky variable is x in solution of quadratic equation. So x in a function of u has two square root branch points. And for the purpose of a symptomatic special relation, they are implemented by a shortcut. X plus x minus standard definition, then the special relation is given in parametric form, either to piece of this form. So E includes x plus and x minus. This is cut to x minus, this is cut to x plus. So the Riemann surface of energy as a function of spectral parameter u has two square root cuts. Okay? And we know what does it mean. This means that sensitivity, this is torus. And we can resolve this diagonalization. And back in 2006, 2007, many different authors actually seriously considered this array, and you can find papers with utility function aside. And I remember in my very first paper, I actually learned the utility function for the purpose of computing one number. However, if you dig further, you realize that for many reasons, I give only one of them, elliptic penetration doesn't phase the game. Because one of the reasons that we have Dresden phase. So in the asymptotic Riemann sheet, you have only two cuts. If you go through this cut, you have to discriminate. We already used this property in back to 2007. It was more clarified and the solution process was given more explicitly. But actually, I think many people here in the audience use it in one way or another, implicitly or explicitly in many different ways. So it's true that because of Dresden phase, you have to understand that analytic dependence of spectral parameter in IGST15 involves infinitely many branch points. Genus Riemann surface, and you do not should expect to introduce any nice parameterization. So There were several attempts to express this in phase some effective project. They have some progress, but I cannot say that like established as completely successful. And another thing I would like to mention that actually this U spectral parameter is the right parameter. For instance, pulses that are smartest are situated on distance I. Or if you go to the quasi-classical limit, you have correct post construction with this spectral parameter. So you actually do not want to parameter in order to retrieve branch points. We want to keep them and also have branch points. So really, conclusion, I want to stress that we should accept that the branch points are there in the IGST integrability, and we have to learn to live with them. And based on the progress of the last 5-6 years, people indeed did this, and they learned how to do this. Now I change a little bit perspective, and using IT famous phrase, branch point is not the bug of the system. This is probably the main feature. When you have a branch point, you have a luxury, which is parametric function. You can make analytic continuation around branch point. For instance, if you have differential with some singularities, monitoring around these singularities give you rich information about solution of differential equations. And there's a whole business of mapping monitoring data of differential equations to actual solutions. So here, I mean, conceptually, this is something stress. We have branch points, so let's go around this branch point and learn what we get. And use it as our benefit, because before we didn't have. Well, I do not do this with the web functions because web functions composite objects, and there it's quite messy. As it turned out, after several years of research, web object is vastly like Q functions. So we have Q functions, there's not only one Q function, there are many. 256 is 2 to the power 8, was the case of IGST15. And there are some branch points there, and conceptually, you take this Q function and go around. Going around branch point, which is position of the device G, we denote by T. So this is analytic operation which you do on the QC. Now, on the other hand, for the Q system, there is one very specific discrete algebraic operation which is over star, and it's actually related to automorphism J and algebra. Basically, if you take generic EIJ and this transformation, so this stuff has something to do with this operation. It's very specific. I will discuss it a little bit later. So the claim that you can put this kind of equality between these two things. Linear continuation amounts to this very discussed algebraic operation. And I would like to just stress the idea that we should think about IGST spectral cap as an algebraic system in any standard, absolutely standard one, plus this additional equation, which in some cases actually even goes out as a crossing equation. Okay, so just notice that this equation is a concept. If you just want to be more precise, I have to spend more time to discuss what I mean by this equation. This is a conceptual idea. Now, before making it more explicit, more than define this equation, I think I have to give some review, status report about what was achieved by quantum curve, because it's in the past 2 years now since we presented this first time. What was the achievements? I will give you. On the way, I will tell you some more and more details about it. For those who not want to do business, I just very brief what we do. What is called quantum spectrum? Well, there are two things. Quantum and spectrum. It's called quantum spectrum because it computes quantum spectrum of certain field sphere. So it's a IGST dual pair with an equal force T coupling, a strong coupling, and everything is in the tooth large ladder limit. So the only parameter is down, tooth coupling constant, or G is fused. The spectral problem which we solve is to find conformal dimensional slope operators or energies to string space. this object organized into unitary multiplex of symmetry algebras, which is PSU to /4. And actually, for superalgebra, if representation is unitary, it's also highest rate at the same time. It's a very special feature of superalgebra. And therefore, you can characterize unitary representations by just highest rate, rate of the highest rate. In this case, we can use 6 charges. 3 of them can be in J1, J2, J3, which is rotational charges is 5, and 3 other charges per years. Here, J1, J2, J3, S1, S2 are integers. They quantize, so the real problem is find conformal dimensions in the functional problem. So this is what special problem is. This is how special problem is formulated. So now, so quantum spectrum explained by now why scale? Because it's actually Riemann-Hilbert equations. So how they formulate? So indices A and B run from 1 to 4. We have 4 functions P, A is lower index, 4 functions A is upper index. They have the property that on a certain Riemann sheet, if you connect Einstein minus 2G and 2G, there is only one cut, there is no other cuts. And there is another function. And these components of the mathematic are periodic. And Riemann-Hilbert equation which defined for us per curve are this one. P above the curve is linear combination of coefficient of mu of P below the curve. And discontinuity of is given by this combination among the integrated and continuation of branch point. So these are Riemann-Hilbert equations which constitute the quantum spectral curve. And because we want to be we do not want really simple setup, we want to go everywhere complex plan and write the same equation between
And what do I do to match this with your previous equation to deal with it?
I'm coming to this. So this is Riemann-Hilbert problem. We have large question topics. This is Riemann-Hilbert problem, how it's formulated, and now we have supplemented this boundary data. Boundary data is saying that we want solution which power like behavior. U goes to infinity, and we have some asymptotics. A is these coefficients, and some lambdas, and also we want solution which do not have any poles. Standard category. So the game is find solutions with these properties, and then they map into spectrum of IGST15 by this relation between lambdas and charges. So you get the conformal dimension and all the charges. That is how we solve spectral problem in a spectral curve, at least conceptually. Now, I briefly review what things we can do explicitly. So there are canonical questions which we can address. So, canonical question, okay, let's find some numbers for spectrum. We can do analytic solution. We can ask how to do analytic solution of weak coupling, we can ask how to do analytic solution of strong coupling, and also try something that I find probably needed. So what is done? So our main contribution is my PhD student Christian Marou. We did analytic solution of decoupling in some cases. In the next talk, we will learn what is done for analytic solution of decoupling. Back to 2 years before, I presented my results on this conference, and now what we have improved a little bit. We have 10 loops and give the whole into sector. This means we can choose two charges arbitrarily. You just go online and download our paper and automatic attachment, and you just black box which focus for those numbers. So you see you can go up to 10 loops. So you choose length of operator, spin, choose type of solution, and this is an example. For example, this Baxter polynomial has this most dimension of 8 loops. For Kanishi, we pushed the computation up to 8 loops. This is how I have 10 loops. This is how it looks like. There are some interesting attenuation of progression theory on the multiple zeta values, and also we observe that only special combination of multiple zeta values appears, which were predicted by Oliver Schnatz and later discussed with the papers of Francis Brown. So not arbitrary multiple zeta values appear in this answer, but only this combination which falls in the value of multiple zeta values. For the moment I did observation, I can comment maybe how to prove it. I cannot prove it yet, but I have some ideas.
And what is special about those combinations?
Ask me at the end of this is also special. Okay. So what we still do at decoupling, so the first one stays. Now we also expansion in brackets. The point is that at the moment which we're using, okay, algorithm that we're using with respect to the expansion, so each iteration goes by one. It's very quick, but go by one. But we also know that the evolution approach with goes in brackets. So in principle, we have to combine to make things in that expansion in brackets. We can say something a lot about it. For instance, we can completely sum all the green terms. Here, they use the combination distance. This result is in the cell around 2013, I think. Well, we want to establish, and also we want to precise construction cells. There are several motivations. One of them is to accomplish, first of all, spectral problem is something that will last 10 years of this conference. Okay, we get some questions, but do we write answer or not? Yes. Multiple interval. Actually, and it's very common idea that, and I completely agree with you, that actually only by doing explicit configuration actually we clearly understand what's going on. And there is one interesting thing which really motivates me here, that now there is a big problem with conformal bootstrap, which says that we can on this conformal dimension of the theory is mostly numerical method, and by doing this explicitly, there is some reference point of analytic computation. Okay, so because I don't have a lot of time, I skip IGST15. After this work done.
Can you discuss how this can happen?
You want, okay. So it's open question, but let me explain why this open question is quite optimistic. So you see, using periodic function, and when g goes to infinity, has become very close to one another. So periodic function becomes a constant with exponential precision. Well, with exponential precision, the three-modular problem is easy to solve. So we are very happy about this. The problem related to this curves, because we know the problems, the three-modular problems that can write solution, but with a little coefficients.
Sorry, it's only the constant between the branch points.
Right, right. But this equation is quite nice. This equation is exactly what we need. So the real problem is to fix coefficients of these curves.
So mu is a constant, but mu is nil.
It's a good question. Well, for p it will be square root the answer, but it will be square root the singularities. Okay? Right. One is square root, one is square root third, one is square root coefficients. So to fix this coefficient, you have to go to double scalar region, and then you have to leave the equation system line. And this is really tough.
Sorry, I couldn't understand that whole why you say that then simplification. So mu is a constant, and then we deal with one of it.
Okay, so mu is a constant. Then this equation gives it to constant p.
Okay.
So
The second one.
second one we don't use. We just put numbers for this solution. Now, when you solve this, you have unknown coefficients. To fix this coefficient, you have to make double scale in this region where branch points are right from another, and use second equation, which is nonlinear. This part is hard.
It can be any power of square roots, not just square roots.
Yes, it can be any power of course, yes.
It's an infinite series of
Yes, yes. The point to find coefficients. As nonlinear strings, I don't know. Okay. So,
what is the analogy? You had a last line. Analogy with something.
I have only 5 minutes, that's all.
Oh, it's an open problem and so on.
Yeah, that's it. Okay. So, now another thing which you can do with analytically continuous solution. The thing which I want to mention here, so further probably will say a lot about the condition vagueness. I would like to mention another thing. When lambda goes to negative pi, we have a right special which appears also in the case of matrix models. So somebody has to go to this point. Now, we can consider, somebody should consider that the system is different with boundary conditions. So this one like was discussed. And primary degree systems, the idea that PMU system on the clock will be the same, but we have have to introduce different boundary. There are many different informations. Question to our tutorial. Can you please use the same method? I'm lost. I'm really lost. So you have many deformations. What's very interesting about some of these deformations is the positional branch points moves. And positional branch points depends on parameters of deformation. And there is very interesting question. And finally, we can note twist deformation. Now we are accomplishing what is in North Carolina. So apart from this, and then we'll just briefly mention what we do here after I explain why concept of purpose also exists. Okay. So I introduce very quickly this system for you. So consider unhand funny difference equation like this. So in any equal to standard Boston equation. You can, if you know solution of this equation, you can write this equation in this determinant form. Because Q should be linear combination of Q1 Pn, so should be so. Now let's pose a question. Suppose you know one solution of this, for instance Q1. Can we find, can we simplify the equation? And the answer is yes. You know from the positive differential equation, if you know one solution, this is going to reduce the random equation by 1. This, if we'll put another, new solution is some function times Q1. And you have to find this function psi, and for psi, for derivative of psi, or in this case, find the difference of psi, you can write equation of 1 and plus. Okay, so Q is equal to psi Q1. W is just basically after some normalization for continuous discrete derivative of psi, and there is the very important to check if original equation was like this or unintended equation. So W will satisfy this and minus 1 equation, where QAB is given by this combination. And we can iterate this procedure. For instance, we have rank equation by finding one solution and constructing QAB by this combination. We can rank times 7. From rank 7, if we know one QAB, we can go to next order. And so we reduce our problem, at each step we reduce our problem one order by less. In each step we gave some funny difference equation in the first order. So what we are doing, we are solving our equation with quadrators. But when we do this, at each step we have to find solution of this recursive relation, which people can recognize into Q relation. So Q is many indices, it should be completely isolated. So what I want to emphasize, so this is so Q function satisfies this property is called Q system. I wanted to emphasize that constructing Q system to solving some funny difference equation with quadrators. That's what actually Q system is. Now, in this language, it's quite easy to write what is twisting of the Q system of an individual model. You see, when you introduce you have to choose basis of your solutions. So you have rotational symmetry, which rotates the basis of your solution. So because they're local, these rotations should be global. But let's engage them. Let's put the exponent here. If you put the exponent, you can check it corresponds to making twist in your model. So gauging rotational symmetry of your solution is introducing this. This is basically the idea about twist. Okay, now finally I can tell you what is Q star. You see, if you carefully look at this relation, it's invariant either going up or down. So Q star is basically saying, if originally I read the diagram up, I can read it down. This is Q star, and I call it Hodge duality. And finally, last thing, we are not obliged to go in one direction. We can sometimes go down, sometimes go up. And very simple thing, what happens is actually a supersymmetric system which appears. So if you choose these guys going in this direction, this guy going in this direction, you have a supersymmetric system which usually is this form. And actually, we do not need to follow this line. Actually, we have all the zoo of Q functions which satisfy Q relations. And we can choose arbitrary passes we want, and we get anything in there. can be more precise about those features. So we have IGST15 and also Hubbard model. From TBA, already a new system of what's got in the way I show you was conducted for the bridge to H4, for this was IGST15, and also for Hubbard model. Right? But it wasn't constructed for this IGST. Now, what I suggest to do is let us not try to TBA. TBA is complicated. Let's just try normal algebraic system, which doesn't combine branch point and impose this condition. In the case of this guy, we know that it works. Now, in this case, so far it wasn't done, and my best hope that if you do it here, then we will know the answer without doing TBA, which is apparently complicated. So what I did, I checked this for Hubbard. So I started from simplified system case and impose this condition. I did not write real or something like that, and just try to impose this condition, and what we realized, there are two possibilities. Either we get two systems which do not have branch constant at all, just is given by this equation. So what is the difference? There is important difference here and here. In this case of IGST5 process 5, sum over k is equal to 0. If we are trying to pose this equal to 0, in the case of Hubbard model, we actually get our system is trivial. It's no interesting solution at all. So we have some here. We want to put this here non-zero. What does non-zero correspond to? This non-zero corresponds to the p-function at this point should not be equal to 1. In a case 5 versus 5 case, this p-function is equal to 1. And we want that in this case it's not equal to 1. When it's not equal to 1, then look, in this case, analytic implication of branch point should flip this p-function to this function. If here is 1, here is 1, then it's clear. In the Hubbard case, here is 1, here is not 1. So analytic implication brings 1 from this to 1 to non-trivial function. So we actually have to rescale all the system. And the function f actually performs this scale. So the difference in this necessity to rescale in the case of Hubbard model, which necessitates have. And then we have the similar situation. We use the same, an equation for PTB equal to P is modified in this way. And that is what consistently has some limit to the data. So to conclude,
sorry, is it the same set of equation as what was derived from TB?
Yes. So it's the same set of equation. Now very interesting point. So in the case of derivation of TBA here, you see in my case, mu is function with infinitely many branch points. F has not that many, but still is a combination with infinitely many branch points. Whereas in the case of derivation of TBA, it's exactly the same equation. Here, except that here it's a function which is very simple. It has only one branch count. So it's not exactly the same, but what is the difference? You can redefine P that this function has only one branch count. But the price we pay for this, that this becomes very analytically complicated. So in the symmetric case, when we want this function and this function has good analytic property, you should stick to this answer. Conclusion. Also, even in the case of IGST5 still has many undeveloped explicit applications. I want to emphasize the branch point in this case, not a bug but a feature. And we have this nice conceptual equation. And I propose this equation tries to decode this IGST2 case, and there is obvious places to work on.
Time for a couple of more questions, please. About your maxing, in the Hubbard model, definitely the branch point is a 5. In the Hubbard model, the branch point definitely is a 5. Any comments on this?
Well, you want to say that we can resolve it. So here is this, okay. Hubbard model, but homogeneous Hubbard. You can take any different homogeneous group of infinities or reduce to one. So you're right, it's a homogeneous Hubbard model. So you can stick this source term directly to IGST15.
Yeah, so you have a list of models, IGS5, IGS4, IGS3, then Hubbard,
Yes.
data connection. So what about other models, in-chain sigma models? What's
Yeah.
the criteria for someone to
So my general idea, which I do not develop everything, I just try to make an idea. So you take a favorite model and write the system for this model based on symmetries. You can take rational case, for instance, how it looks like. Then you say you have to find a good way to introduce branch points there, and you say that when a branch point induces some automorphism of this. So if we are able to do this to any model, it will be perfect. Now, so far when I try to do it technically, I need two sets of functions. Like cosmonic and thermodynamic. So because this is actually complicated, I need two sets of functions. So therefore, if you have only cosmonic models, I just don't know how to do this construction. But if you have at least like symmetry algebra times symmetry algebra and under analytic definition you exchange them, which may be actually this case, then at least I can suggest what to try.
For example, it seems like to have a special point where you have a branch point, you can also have Lorentz invariance, otherwise you have full symmetry. For guessing which models would be. So, for example, can we add Lorentz invariant model?
I don't think so. I don't think so. And the model, and the Lorentz bias is here. In Lorentz bias, you can put that as multi-dimensional difference. When the dimensional difference, you already have problems immediately. You don't have branch points. So this is one idea that constructs a class of individual models which have branch points. And use it like this. It should be a new class.
Do you have any comments about lambda equal -5?
Yes, I have. So from the special relation content, this branch point can be equal to this branch point. So if you write here for g is equal to I, is the value of coupling constant g.
Technically, if there's a simplification and something nice to be understood, and if physically it corresponds to something.
Well, I know what happens in the matrix. So in the matrix model case, this point corresponds to the fact that when you make a good expansion, graphs which have variable vertices contribute the most to the partition function. And this is the limit when you make matrix model gravity corresponds. Other thing which I know that negative partial cost corresponds to going from magnetic to DC space. I mean, that is R square, right? You have the negative to minus R square. That is, we can speculate about this. So, I mean, this point number should happen in DC space. Well, this all almost happens. No?
Okay, maybe the last question. You talk about the Q function, right?
Yeah.
Any use ideas about the Q operations? How to define and decline this? Because it's good like hidden waves of certain operations.
Alright, this looks like.
And
beyond one loop, we operate a model construction. And it will be back beyond one loop at recoupling,
right.
if you operate a model construction.
Okay.
And it will be
You
very nice about.
You operate for the spin chain, right?
Yes.
Alright. But from the sigma model side?
Also no. So it will be very nice to do this,
Yes.
but it was not done.
To know the so maybe you could verify what you really know about strong coupling. A couple of years ago, maybe 3 years ago, we have one achievement by Sanders and William. I had a conjecture about the behavior of better roots strong coupling. So according to this conjecture, the better roots were divided in basically 2 groups.
Yes.
One group was moving towards the branch points, and the other group of
If we accept the argument that the periodic function become a constant cannot be 0. If it's 0, it's irrelevant. So, okay, beta root is 0 for me. Yeah. Beta root is 0 for me only. Yes, it's true.
Actually,
your beta root is 0 for me only. Okay? The data root we're speaking about is 0 for me only, which is by either.
what is the beta root? Is it 0 for y,
1, 0.
1, 0,
Yeah.
now we have two zero functions, they have a 0 somewhere.
But roots are high definitely on the difficult.
Yes, so there is 0, 0, 0.
These are points where y functions take into minus 1.
So 0 for me.
The zeros? Right. But on the physical sheet. So here is connection of mirror sheet to physical sheet. Okay. So zeros of me here will be beta. Okay. Now, if mu is constant on this line, it cannot have zeros there. So there will be two. This point. Yeah, for the second group, let me tell you private. I will focus on too much details.
Okay, so I allow myself a small error. The name of the quantum spectral curve has a double meaning. First, of course, it's a spectrum of this model. Second, that the classical spectral curve is in fact the characteristic equation for monotony.
Yes,
one which computes the quasi-moment. It's worth noticing that the Q functions are analogs of quasi-moment, or related by a simple formula. Okay, let's take D. Okay, next up will be further numerical solution of the spectral problem. Next to leading created and
Okay, so let me move the start at this point. So first of all, I'd like to thank the organizers of this conference for giving me an opportunity to speak here and present my results. So my talk will be based on these two papers in collaboration with Nikolai Gromov and Grishka Sito. The first one is already on archive and the second should appear soon, hopefully in a few days. So in both of them, we use the quantum spectral curve for n equals to 4 super Young-Mills that Dima just described to study two different problems. In the first one, we developed an efficient numerical algorithm for solving the equations and getting the spectrum with a very high precision. And in the second one, we analytically computed the BFKL eigenvalue at the next to leading order, which has never been computed before. Well, the quantum spectral curve is a simple set of finite number of equations of Riemann-Hilbert type, which are the fact that it's a finite set, the quantum spectral curve has led to many analytic results, both in this model and in AGM, at weak coupling, strong coupling, various perturbative expansions, and so on. And of course, since it's only a few equations, the natural step is to try and solve them and find a coupling numerically. Some of the reasons why this is an especially interesting problem is that here we can go beyond the few states for which thermodynamic Green-Hansard equations have been worked out, and study numerically any state in the spectrum. And moreover, also in contrast to the TVA, quantum numbers are the integer here because they enter only in the asymptotics and some algebraic relations. For instance, we can consider the analytic continuation in the spin to negative values or even to complex values in a very direct way. And one of them, the interesting regimes, is the FL when the spin approaches -1. Let me briefly describe the numerical method we use. We start from the simplest ingredients of the quantum spectral curve, which are the key functions. I'm going to describe the algorithm for generic state, not necessarily SL2. Then there are P's with lower index and with upper index. Their key property is that they have only one branch cut on their defining sheet, whose position, the branch point's position, is determined by the coupling lambda. And so there are asymptotics in called the S5 conserved charges of the state. Since they only have one cut, we can resolve it in terms of the usual Zhukovsky variable and write P's as a series in this variable. Then the coefficients are the key parameters in our numerical method. Once we truncate this expansion at some point, we set coefficients to some numerical value, and it gives an approximation to the P function. Then to close the equations, one eventually needs to consider P's analytically continued around the branch points, and this we denote as P tilde. There are various ways to close equations. We found it's very efficient to switch to Q functions with one index, Qi. They are analogs of the P functions corresponding to ADS5 instead of S5. And to pass from one to the other, one has to introduce Q functions with two indices, Qai, which are determined in terms of P's by this difference equation. And if we have a solution of the equation, Q functions are found by this simple expression. And Q's with one index or two index or all Q functions, they are all analytic in the upper half plane. But in the lower, generically, they have infinitely many branch cuts. So let me describe how we construct them numerically. We will need the Q functions with the real axis a little above the cut in this range. The first step is to solve this difference equation for large U. If U is large, we can plug in the asymptotic series expansion of the Qai into the equation parameterized in terms of some coefficients. And this gives a simple linear problem allowing to easily fix the coefficients. So that is this is an asymptotic series. We truncate it at some point, and this gives a numerical approximation when the imaginary part of U is large, so in the far away in the upper half plane. But then we can notice that this equation relates Q's at two values of the spectral parameter with distance I between them. So if we know the Q at this point, for example, we can use the equation, which is exact, and go to and reduce the imaginary part by 1. And then we repeat this procedure many, many times until we reach the vicinity of the real axis. A good solution there. Then we have to close the equation, and for this we use the formulation known as Q omega system, where we introduce functions that are analogs of mu, which Dima discussed, but unlike mu, they have short cuts, not long. They have an infinite tower of these cuts, and they are I-periodic. So to construct them, we first need Q's on the cut, which we know,
And also we need Q tildes, but they can also be easily computed since QAI does not have branch cuts on the real axis in this expression. So tilde is only applied to P. It amounts to flipping x to 1 over x. And omega is fixed from this equation, omega tilde minus omega is equal to some combination of q's, which we know on the cut. And because of this, we needed to solve this equation as an integral of the right-hand side with the usual cotangent curve. In principle, there are also some zero modes, which by now are very well understood for integer and for non-integer string as well. Then the final step is to actually close the equations. So for that, we use an independent constant, which says that once we know omegas and q's, we can compute q tilde in this simple way. But remember, we already had an expression for q tilde in terms of q with two indices and p. So these are two different ways of computing one and the same quantity. They should give the same result if we have a true solution. As we are working numerically, they will not match exactly, but our goal is to minimize their difference. Some sampling points on the cut, evaluate the difference there, and well, sum over all sampling points. This is the function which we have to minimize. The function by the coefficients appearing in C, well, and also by the conformal dimension. Yes, chart is obvious. And this is just a problem of minimizing one single function of some finite number of arguments. So for this, there are many efficient algorithms. We found particularly effective to use the Levenberg-Marquardt algorithm, which is the iterative procedure combining Newton's method and gradient descent. Let me show how the algorithm converges. So very often it manages to converge from even a rather remote starting point, and the value of this function that measures the error drops off extremely quickly, in addition to the fact that this computation also takes quite a short time. For instance, for Canicia operator, some value of the coupling, it took only 30 seconds on his usual laptop to converge to this value of delta, with a precision already a bit higher than the TBA. And, so the convergence is double exponential, and roughly speaking, the number of digits of precision we have is doubled at each iteration. Well, as a test, we computed the Canicia anomalous dimension in some range of the coupling constants. So here we have results with at least 12 digits of precision. And they, of course, match with the TDA data, but are much more precise. Eventually, we hope to compute it with an even higher precision and fit the strong coupling expansion.
Why did you stop at 2?
Because we switched to other things, which I will explain now.
Because it's just a few seconds.
Well, but all the other things also took us a few seconds, and in the end it combined. So we will surely return to this. So the question which we found of great interest is to consider analytic continuation to non-integer values of this field for SO2 sector operators, in particular for twist 2 operators built out of scalars and S covariant derivatives. Typically, the picture which describes the relation between spin and anomalous dimension for them, maybe you've seen it already, it looks like that. So S is a function of delta. When the coupling is 0, it becomes piecewise linear. So this line is just the classical dimension delta equals S plus 2. And then when S reaches -1, it bends because of the DFKL singularity, and S remains equal to -1. Well, and then it's continued as an even function to negative values of delta. So one can plot here I plotted the strong coupling expansions or weak coupling expansions. With our method, it's not a problem to plot the curve at some finite coupling. Let me also this region around x equal to -1 is expected by kind of data ansatz itself. So somehow different from the usual asymptotic data ansatz. But then the more interesting thing we can do is to go not only to negative values of the spin, but even to complex values. So then it is expected that there should be some cuts, and the whole function S of delta should have a complicated analytic structure. And here we have explored numerically two sheets of its Riemann surface. So this is a three-dimensional plot generated from some cloud of numerical plots. So the upper sheet corresponds to the picture I showed before. So a part of it is the curve S of delta. And then we found that, as expected, there are some branch cuts in the vicinity of S equal to -1 at weak coupling. When we analytically continue through them, we can do numerically by just taking small steps. We arrive to another sheet, which we have also mapped. It's shown in darker colors here. And on that sheet, there are again many cuts, some of those that were not present originally. So these red things, they show the positions of the cut. So this is an example where we compute the conformal dimension directly for complex values of the spin. In addition, we try to probe the rather extreme regime of the BFL intercept. So the intercept is basically the value of the spin for which the anomalous dimension becomes equal to 0. So it is the point at which the curves intersect the vertical line. It is itself a function of the coupling, and in this regime some of the key functions diverge, but using a rotation and rescaling we can construct finite combinations out of them and apply our method again without many changes. So this led to this red curve, which shows the BFL intercept as a function of the coupling constant in a wide range of the coupling constant lambda. So this kind of result, as I understand, is at the moment only accessible using our methods. So the blue curves show the expansion at weak coupling here or at strong coupling here. And our curve, of course, interpolates between them. So here we computed the intercept with about 10 to 15 digits precision. Later we focused on the weak coupling region, as I will show. So now let me discuss our results of the upcoming paper. A priori not related to numerics, we used an analytic method to construct the BFKL, the eigenvalue at the next to leading order in the coupling. So exploring the BFKL regime is, of course, a long-standing and important problem in n equals to 4 super-Young fields, which has evaded solutions for why the ratio is healthy. In this regime, the anomalous dimension effectively receives contributions from all loop orders of the theory. So the spin as a function of delta has this structure, so it's -1, and then there goes a weak coupling expansion with some functions Fn of delta. So we have F1 for the G squared, F2 at G4, and so on. In the first order, also let me mention that, of course, in this regime, many similarities appear between n equals to 4 and QCD, which is another reason to study. In particular, the part with maximal transcendentality is in the results for n equals to 4 to 3 and Nielsen and QCD. So the leading order in this expansion was computed quite some time ago, and it is just a simple harmonic sum. Well, the harmonic sums are defined like that generically. Here we understand that it is continued analytically from its values at even harmonies. It can be reproduced from integrability completely by directly solving the quantum spectral curve equation. And then at the next to leading order, the expression usually found in the literature makes one to stop looking at this limit for the rest of one slide. And because it's extremely complicated, it has some kind of infinite sum and so on. But for instance, in this paper, and perhaps in others, it was understood that in fact it's also a simple combination of harmonic sum. So now we have transcendentality 3 in each term. It's product of harmonic sums and some numbers like zeta 3, pi, and so on. So it required already very involved calculations to proceed to the next leading order. And at present, the computation of next leading order has not been done and probably will be even more involved. So our main assumption that we will use to compute it is that again, only harmonic sums multiplied by some simple coefficients will appear here, and by analogy with the leading order and next to leading, the transcendentality here should be 5. So let me first present the result that we found for this function x3. So it looks like that. Just a combination of about 40 terms, all of them involving harmonic sums, and each term has transcendentality equal to 5. This from an iterative analytic solution of the quantum spectral curve, which I would like now to describe. First of all, we write down the most general form the result would have. And so we combine all harmonic sums with transcendentality up to 5 and multiply them by some typical coefficients like zeta values, pi, and so on. And all combinations with transcendentality equal to 5 give us a basis of 288 functions. And then 288 unknown coefficients expected to be rational numbers. And from the quantum spectral curve, we derive constraints on them by considering expansion around the poles of the result at negative positive, at all positive values of delta. So more precisely, even looking at the first leading order term, we could plot it as a function of delta and see that it has poles when delta is equal to 1 or to 3 or to 5 and so on. So the pole at delta equal to 1 corresponds to the usual physical SL2 sector operator, or you could say that it corresponds to the upper sheet of the three-dimensional picture that I showed before. And the coefficients of expansion around this pole can be determined from usual perturbation theory results, which are by now known up to 6, with the latest contribution coming from the work of Dima and his student Christian Marvel. And then around the other poles, one should expect also some kind of operators which are described by some other kind of perturbation theory. So to fix the coefficients, we iterate the quantum spectral curve in the coupling and in the deviation from the called small delta. The p functions are known at leading order for any delta, and then q functions with 1 or 2 indices. And then our goal is to solve this difference equation, which I showed before already, iteratively in g and in delta, starting from the leading order solution. So for that, we developed an analytic algorithm, which once we have some approximation to the q function, so this equation is satisfied, we can improve the precision to which it will be satisfied. So we increase the accuracy of our initial solution. And actually it gets doubled at each step of the iterative procedure. So unlike the method used by Dima, which relies a bit on the fact that we are at weak and it's a near VPS expansion with some p's are small, our method is generic and should allow perturbing any solution. So the key point is to use an ansatz of this kind, where we take the starting leading order Q and look for the exact solution as the starting one multiplied by the function. And then on these functions we obtain a simple difference equation, which can be solved and the whole procedure is repeated, leading eventually to the eta functions of the kind already found that we covered before. So we increase the order sufficiently high. We close using a couple of tricks related to analyticity of key functions. And this gives the result for instance, around delta equal to 5, we found the following expansion in powers of this delta. So involving some mostly very we computed such expansions around the delta equal to 3, 5, 7 and combine them with the known perturbation theory results. And this already gave even more equations than we had coefficients in our basis. So we get an over-constrained system which turns out to have a unique solution that I could show before. A remarkable fact confirming in our opinion the validity of the result is that only 37 out of the huge basis of coefficients turned out to be non-zero. And also they have a simpler form than the intermediate coefficients we obtained in these expansions and so on. So this is already a rather strong test, completely non-trivial, but we did also a numerical test where we computed the anomalous dimensions with an extremely high precision, around 80 digits, for a range of the coupling constant between something like 1 over 100 and around this level. And then we fitted the result with powers of the coupling extracting the coefficients in the expansion. So we did this at 2 points, delta equal to 0, corresponding to the intercept and some random more or less chosen points, 0.45. So we found in both cases the expansion coefficients with a precision of 60 digits. So by making the font smaller, I fit here the intercept, but for the 0.45, I have to split the results into 2 lines. And we found that all of the 60 digits reproduce perfectly our analytic prediction. Moreover, we also got a prediction for the next orders in the expansion, such as a cubed leading order and fourth and so on, with a slightly lower precision, but still quite high. Let me finally mention another extension of the quantum spectral curve we started to develop. So this is its adaptation to the generalized cusp anomalous dimension. So that's the anomalous dimension corresponding to a Wilson line, with a geometrical cusp angle phi, and also an internal angle theta, which measures the difference between couplings to the scales on the 2 rays. It has been very extensively studied, related to divergences of different kinds of amplitudes and so on. In particular, from integrability, there were equations of thermodynamic data of that kind were proposed that describe the anomalous dimension exactly at any value of the curve. We managed to construct the corresponding quantum spectral curve equations that reduce the problem to a finite system, to which, in particular, our numerical methods should be translated quite smoothly. So essentially, the main point is that P functions and other Q functions acquire exponential asymptotics related to the angles, and also one has to go to higher orders in the large Q expansion than in the usual theory to extract the conformal dimension or other character. Well, and so in Dimo's talk, he also showed some examples of deformed theories, although probably without the characteristic dressing phase, which is another difference of this setting compared to the usual spectral problem. So as a test, we consider the near BPS expansion, the deviation, expansion of the dimension in the difference of 2 angles, The first term was computed at any coupling by a variety of methods and confirmed from integrability. And we managed to compute the second term, also at any value of the couplings. We found some explicit expression that matches the perturbative theory predictions in particular. Let me now conclude. So our numerical method gives quite drastic improvements in speed and precision compared to TBA, and works even in such extreme settings as the DFL intercept or analytic continuation to complex spin and so on. And in addition to this, we developed an iterative analytic method which led us to results for the next to leading order DFL eigenvalue. Some future directions would be to consider the next yet another term in the expansion of the BFL anomalous dimension, which more or less is a question of computational data, as we understand. So then one could ask more conceptual questions such as what is the reason that only such a small fraction of basis elements enters the result, and what is the structure of the general term in the expansion, and so on. Well, also, having this numerical method should help with various analytical, for instance, with guessing the correct ansatz for strong coupling solutions. And this is also, it also could be adapted to AGST theory or the coordinate for potential as strong coupling, where there is a prediction to be reproduced coming from string theory. And finally, we hope that the quantum spectral curve could also shed some light on computational three-point function. Thank you very much.
Thank you, Theodore. Questions, please?
So conceptual question, I mean, of course, Lippertov in some sense started this whole business in the US, this spin chain, this SL2C spin chain.
Yeah.
Can we learn something about this spin chain picture from this approach?
Well, about the spin chain itself, not directly. Well, we can learn, for example, about the Baxter Q functions, because these are the objects that we are computing in the quantum spectral curve. So then one could try to guess what is the spin chain for which they are the actual Baxter Q function. At least one way to look at this.
And just to mention, the DFL regime is very similar to asymptotic DFL set of equations, so we can start trying to incorporate them as numerical deformation of
But it's no longer SL2C, right?
Yeah, it's actually involves all the sectors.
So the same question was asked already. So when it was TPA, story advanced for coupling, only we considering and not converge.
Yeah.
So how far you want to compute constant and still be conversion?
How far our method is intended to small coupling?
Yes.
Well, we didn't really push it, but given that we had such high precision, even in extreme conditions, we hope that we could enough to get new analytic predictions.
No, but so you don't feel so?
No, but so far we got to G about 2, because we focused on the FKL.
Well, it's a related question. So I have this operator with J equal to 4 and N equal to 1, and this operator has the critical value of G at very small values of G, less than G equal to 2, which is your favorite experiment. Can we try to do for this operator?
No, we can't. That's
so
future.
You should do it. You can do it right now. It takes only 2 seconds.
Not right now.
We are going to release our code at some point, so everyone is welcome to compute his.
Careful to understand your algorithm.
Okay, I will, since I don't see any more questions, I will ask the question. Usually for other methods, it's very difficult to penetrate into the structure strong coupling regime. For example, our old calculations with TBA suddenly get slowed down or even unstable. But here, what does stop you from, to what values of lambda can you go until it breaks down, and why?
Well, so far we went and one that didn't break down, not to be but well, it starts to converge, I would say, slower than it did before. But we certainly would hope that it can be pushed farther away.
So you have lambda now to cosmic values and 1,000.
D equal 2 or 100.
And you can measure many terms of strong coupling expansion.
Yeah, we didn't really focus on this yet. But yeah, so here, for instance, in the next step, there are more.
Okay. There are no more questions.
So unfortunately, due to the wet outside conditions, we should do our reception at the Great Hall, the same place where we can report today. But still, we hope to get the live